Hello, thanks for your interest in our work. I'm Jia from the Ohio State University. In this presentation, I'm going to introduce our optimizations for sparse convolution neural network inference on edge devices. Specifically, we target to expedite the inference of proven CNN models on multi-core CPUs of small IoT devices. We find this task important because, first, researchers discovered the redundancy in CNN models and have been working on weight pruning for around half a decade. The effectiveness of such approach is field-tested. Secondly, although powerful edge devices equipped with GPUs or neural accelerators are common today, most pervasive and inexpensive IoT devices do not have such capabilities. To achieve this goal, we seek inspirations from prior work including weight pruning, layer fusion, and inference of pruned models. Then, a novel inference scheme is developed to fully utilize the power of these methods, while avoiding the overhead of previous design or implementations. We also thoroughly optimized our implementation and successfully mapped it to multi-core structure. Finally, we experiment with various popular models and compare our performance against previous sparse CNN inference scheme in the same hardware context. Now I would like to give more details on the background. As CNN became a hot topic, almost everyone amazed by its general learning capability was also bothered by its efficiency. The complexity of CNN inference is proportional to the product of each input and model dimension. Think about that. Well, the training process is probably more disastrous, but fortunately we will not focus on that today. As we can see here, to calculate just one output pixel at nxy in the inference process, each channel of kernel n will be aligned with the xy coordinate of corresponding input channel. Then each aligned pairs of weight input pixels will be multiplied and summed up. So at the end of the day, if we are running a popular model of VGG16, for example, we will have 10 gigaflops operations. That is tremendous. To make things worse for small devices, conventional implementation of CNN inference is based on general matrix multiplication. This involves a pre-processing called image to column. So this image to column transforms a convolution problem to a standard matrix multiplication problem. What it does is basically it flattens each convolution window in the input feature map to a vector. So as we can see here, this process actually duplicates the input feature map. So it is very spatially expensive. To reduce the complexity of CNN inference, researchers have found we can prune out certain weights from CNN models with acceptable performance loss. These approaches are called weight pruning, and they fall into two major categories. The first is non-structured pruning, which prunes out individual weights as needed, leaving irregular zeros in the weight tensors. And the second is structured pruning. It prunes out weights according to some regular patterns. For example, here, the channel pruning can remove a whole channel from the weight tensor. So the pros and cons of these approaches are pretty intuitive. The non-structured approach is more flexible and therefore yielding higher sparsity under the same accuracy loss. The structured pruning, on the other hand, leaves more structure sparsity in the weight tensor, so it's more hardware friendly and easier to optimize. Since there is an existing body of work on the inference of structurally pruned models, and the fact that non-structural pruning yields better accuracy, in this research, we want to focus on the models that are non-structurally pruned. Another work on layer fusion aims to speed up the inference of CNN by evaluating multiple layers at a time. It performs convolution on partial input, and the outcome is immediately forwarded to the succeeding layer for the same convolution process. This implementation yields better locality and lower spatial complexity, but it involves more complicated control flow. Specifically, since the evaluation windows are overlapped, a cache of intermediate results needs to be maintained. To fully unleash the power of non-structured pruning and fused execution on mobile CPUs, we developed a novel inference scheme called fused DSConv based on the idea of direct sparse convolution. Direct sparse convolution was first introduced in Scheme Cafe. It is specially designed for the inference of non-structurally pruned models. As we can see here, for a given kernel, it picks out the non-zero weights, and for each non-zero weight, it is multiplied with the area it will be applied to in the convolution process, and generate a partial result. Finally, all the partial results will be accumulated. So this forms a gathering data flow. The advantage of this approach is that first, it improves the regularity of access pattern in the inference of non-structurally pruned models. And secondly, it avoids the space-consuming image-to-core operation in the traditional matrix multiplication-based inference. We applied the idea of fusion on direct sparse convolution to improve the locality and memory performance of non-structurally pruned models. Meanwhile, we want to minimize the overhead of control flow of layer fusion and the overhead of retention mechanism of intermediate results. Furthermore, we want to make our design scalable on multi-core CPUs. In our work, we choose to implement a two-layer fusion, as the overhead is easy to control, and the layers in most pre-trained models can be grouped by 2. For the first layer of fused inference, we perform a window version of standard DSConv, while the case is more complicated for the second layer. Unlike the first layer, we do not have access to the entire input. Instead, we only have a limited window, here shown in purple. In this case, if directly applying DSConv in the second layer, we will create a coherence for adjacent windows, which will add overhead for the retention of intermediate results and add complication to tiling. Therefore, we design a new process called reverse DSConv. Intuitively, this process is a reversed data flow of standard DSConv. As we can see, different non-zero weights will be multiplied with the same intermediate window in purple, while the results will be scattered to different offsets in the final output, and the overlapping part will be accumulated. To minimize the size of cached intermediate results, the loop order of the second layer is also carefully adjusted. Specifically, since the first layer performs a kernel-wise convolution, the intermediate results are filled channel by channel. Therefore, by adjusting the reverse DSConv, which is the second layer, to channel-wise, only one channel of intermediate results will be cached at one time. Naturally, the compression format of the sparse weights will also be adjusted to channel major for the second layer. This minimized cache size can greatly improve access locality and reduce memory requirement. With the previous design, now the fused DSConv process can be tiled according to windows in intermediate cache, as shown in solid and dashed purple squares. These squares will not overlap, so the intermediate cache for each tile will be independent and therefore easy to maintain. These tiles can then be mapped to different cores for parallelism. There can be minor data risks in the accumulation of final output, but by scheduling a few adjacent tiles to the same core, the risk will be very rare, since the conflicting tiles will be staggered temporarily in their each job queue. Furthermore, due to the regular pattern of access, we also optimize the code with Neon SIMD instructions for ARM processors. Finally, we want to talk about our experiment. We selected 3 CNN models in our benchmark. First 2 are popular models in computer vision, VGG19 and ResNet34, each with 224 by 224 by 3 input. The third one we want to simulate the case with very large input. Therefore, we generate a synthetic model with 16 times the input feature map size. All the probe models are generated by random pruning so as to ensure the generality of experiment. The inference schemes tested are original direct sparse convolution, fused direct sparse convolution, and CAFE, which uses general matrix multiplication for sparse inference. We use 2 hardware platforms. The first one is a Raspberry Pi 3B equipped with quad-core ARM processor. And this is to simulate a standard IoT scenario. The second is an Amazon Cloud server with 16-core Intel Xeon processor. This platform serves for the scalability test. First, we compare fused DSConv with CAFE on Raspberry Pi using all 4 cores. For models with high sparsity, a speedup of 5.8 times can be observed for ResNet34. For the other models, the memory limit is reached for CAFE. In comparison, fused DSConv can finish all inference in acceptable time. Compared with original direct sparse convolution, fused DSConv shows a 1.3 to 1.6 times speed boost. Furthermore, fused DSConv also shows comparable scalability. To study the scalability beyond 4 cores, we run fused DSConv and CAFE on a cloud server with 16 cores. Since fused DSConv is not optimized with Intel SIMD instructions, on 1 core, CAFE is 2 times faster. But we can say as the number of cores grow, fused DSConv shows better scalability. Specifically, on 16 cores, fused DSConv is 1.5 to 1.9 times faster than CAFE. All the above experiments are under 95% sparsity. So here we want to vary the sparsity and see how our optimization compares with original direct sparse convolution. As we can observe here, for all 3 models on Raspberry Pi, fused DSConv constantly outperforms direct sparse convolution with a speedup of 1.2 to 1.6 times. Furthermore, in the ResNet34 experiment where CAFE won't time out, we can see a clear advantage of our optimization over CAFE's under sparsity beyond 80%. Finally, we would like to show that for models with larger input, fused DSConv is more memory efficient. When we limit the memory to 99% of peak memory, we can observe a 2 times slowdown for direct sparse convolution, while for fused DSConv, the impact is much smaller. For synthetic model, almost no slowdown is observed, and for VGG19, only around 1.4 times slowdown is observed. As the memory limit becomes stricter, for VGG19, the performance degenerates quickly for both DSConv and fused DSConv, while for synthetic model, the degeneration is much smoother for fused DSConv. This shows that when the input feature map is large, fused DSConv is more memory efficient. In the end, we would like to draw the conclusions on the performance of fused DSConv. First, comparing original direct sparse convolution and fused DSConv, we can see an average of 1.5 times speedup gained from fusion alone. Secondly, under high sparsity, fused DSConv outperforms matrix multiplication implementations by at least 5.8 times. Moreover, on both IoT and server CPU, fused DSConv shows desirable scalability. Finally, the performance of fused DSConv is much better under strict memory limit. That's all about our work for optimizing sparse CNN inference on edge devices. Thank you again for your time.